So the next few days we'll be dealing with turbo machines. Turbo machines have many different examples of them. So pumps, fans, blowers, compressors are all turbo machines. Same as turbines, also turbo machines. These guys are generally classified into two different subgroups. Groups that add energy to the system. So the pumps, the fans, blowers are all adding either pressure or velocity or some height to the fluid and therefore adding energy. Turbines are taking energy out of the fluid and converting that energy into some sort of shaft power generally. And so you've generally seen examples of these. Airplane propellers, jet engines have compressors and turbines in them, window fans, water pumps, all examples of turbo machines. So generally turbo machines have two parts to them. There's the rotating part called the rotor. Depending on what kind of turbo machine we have, we call it different things. In a pump it's called an impeller, in a turbine called a runner, in a fan called a wheel. So this guy is the thing that's actually attached to the shaft and rotating around. It has blades on it, or fibers of vanes, which provides flow passages, so those vanes are pushing the fluid around, or the fluid is pushing those vanes around to create the power. And then the other part of it is a stator. This is generally a stationary casing or housing around the rotor. Calls have blades. So here we see some examples of turbo machinery. There's a pump in the upper left-hand corner, a centrifugal pump. We'll get to the difference between the different types of pumps in a little bit. But you can see it has vanes or rotors that spin around in a circle, pushing the fluid around. Upper right is a wind turbine, so that takes energy from the wind, converting it into shaft power. And then on the bottom we have a jet engine. On the left picture is the rotor part of it, so the vanes attached to the shaft. The outer part of it is the stationary casing, or the stator, and then you can see it put together on the very right hand side. So there are many types of turbo machines, as we saw a few minutes ago. These are generally classified based on a few different things. Overall design purpose may vary, but they're all kind of designed with the same principles. And so a few things we need to worry about is which direction the fluid is flowing relative to the shaft. So we'll see a couple of examples of those. Whether energy is being taken away or put into the system. So we saw that again a few minutes ago with the pumps, fans and things putting energy in, whereas the turbines take energy out. The other distinction is whether it's dealing with a liquid or a gas. You have different issues related to both. For liquid systems, you have to worry about cavitation or vapor pressure. If there's a really large pressure difference, you can end up having cavitation on one side, and that's not good. For gases, you could end up worrying about really high speed effects, Mach number, compressibility, things of that nature. So here we see an example of a radial or centrifugal type of turbo machine, in this case a pump. So radial means that my fluid is spinning kind of outwards from the middle. So you can see that in the right hand side of this, the flow will come in left and right, as seen on the left, and then the top view of it, it gets spun around, and so the fluid comes out in the radial direction, and therefore a radial or centrifugal flow pump. And here is an axial flow pump, so it's kind of like the jet engine we saw before, where again fluid's coming in left and right, but now it's coming in parallel to that rotation axis, and therefore axial flow. We also have mixed flow turbo machines, which consist of kind of a mixture between axial and radial flows, so not just one or the other, but both. These basically provide compromise between the advantages and disadvantages of the two types of pumps, which we're going to be seeing in the near future. And so you can kind of see pictures down below. Radial flow on the very left, so the axis of rotation is that line on the bottom, and these things will be spinning around that axis, and so you can see the radial flow coming out pretty much straight up and down, so perpendicular to that axis, whereas the mixed or axial flow on the very right hand side, the flow will be going left and right. Mixed flow is some combination, so some angle, not horizontal, not vertical, but between the two. So flow through turbo machines is generally very complicated. You have some 3D motion, especially for the mixed flow pumps, fluid moving in different directions. Also generally fairly unsteady, and so fairly complicated to do the proper analysis, but we can get some basic essential information from something called the velocity diagram. So just looking at which way the velocities go in and out of the pump or turbo machine in general. So we have some notation. The absolute fluid velocity is V, so that's whichever way the fluid is going. Have some angular fan blade speed, so that's my pump or turbo machine turning around. Those blades have some motion. And then W is the relative motion of the fluid relative to those blades. And so kind of assuming that the blades are my stationary reference frame, W is the fluid motion relative to that. So because of that, I have my linear fan blade speed is U, omega times R, R being the distance from the center of my axis of rotation to wherever I am on the blade. And then the actual fluid motion, the absolute fluid motion, is the fan blade motion plus that relative motion. So that is the important equation for my velocity diagrams. So before we get to those velocity diagrams, we're going to be making a few assumptions as we go along. The first one is that the flow is perfectly guided by the blades. In other words, the flow is going in the exact same direction that the blade is trying to make them go, or the fluid is tangent to the blade at every point, especially in the leading and trailing edges, so where it comes in and where it goes out of the turbo machine, that comes in the exact same direction as the blade. This is obviously a more accurate assumption for very long blades that are very close together, because the fluid basically has nowhere else to go, it has to be going in that direction. The other one is that the fluid enters and leaves at the same radial coordinates, so at the same distance away from the axis of rotation, where it comes in and goes out. So these assumptions aren't necessarily true for real turbo machines, but they're, again, generally pretty good approximation, especially if we have long blades that are pretty close together. So here we can see a turbo machine spinning around some axis, as well as its velocity diagram below it. So in the velocity diagram, I have fluid coming in, and you can see the relative fluid velocities W1 and W2 are parallel or tangent to the blade surface, coming in and coming out, just like we assumed. Then we can make a velocity triangle, so we know that my overall fluid velocity V1 and V2 are equal to U1 plus W1 or U2 plus W2 in both cases, and so you make those little velocity triangles, and then from that we can see that in this particular case the blades act to change the direction, in other words accelerate the fluid, so the blades are exerting a force onto the fluid. That force acting on the fluid is adding energy, so in this case, because energy is being added, this particular turbo machine is a pump. And here we have another velocity diagram, this time from a windmill. So again, fluid coming in left and right. I have my relative velocities, W1 and W2, still being tangent to those surfaces on the way in and the way out. Still have my overall velocity, V, equal to U plus W in both cases. In this case, we can see that the energy is being taken out of the system because the turbine is moving due to the force exerted by the fluid. So windmills obviously work because the wind is pushing on them, and so as it pushes on the windmill moves, and that energy is being taken out of the fluid. So going back to a little bit of theory now, recall that the relationship between work and torque, I can relate torque times change in angle to be my work, kind of the rotational version of force times distance. I have the angular version of force, which is torque, angular version of distance, which is change in angle. So however far this thing spun around, times the torque that was applied to it during that time period gives me the total work. Now, if both of these guys are positive or both negative, meaning they're both going in the same direction, they're going in the same direction, my work is going to be positive. If my work is positive, that means energy is added to the system, and energy added to the system means this is dealing with a pump. On the other hand, if they're in opposite directions, one's positive, one's negative, that means that work is overall negative, meaning energy is being taken out, and this is a turbine that we're dealing with. So to find the angular momentum, we can use the Reynolds transport theorem. So we did this for mass and momentum a few months ago. We can also do it for angular momentum. It looks very similar to the momentum equation. For the momentum equation, I had sum of forces. I need the angular momentum, so R cross forces. Same deal here. Linear momentum, I just had V. Angular momentum, R cross V. Rho dV over my control volume, time derivative of that guy. And then over my control surface, again, R cross V, rho V dotted with dA. And then assuming that I have steady flow, so steady flow, this first term is gone as usual. And then in the axial direction is the only one I care about. So in the axial direction, R cross F is basically a moment or a torque. So the force or torque acting on my control volume in this case is the shaft on the torque on the shaft. And then this term I have fluid coming in and fluid going out. So coming in at point 1, R cross V, I get R1 times V theta 1. I want the two vectors to be perpendicular. So R and V theta is the perpendicular velocity to R. So that is my R cross V term. And then rho V dotted with dA, just M dot. So I have that coming in. And then same thing going out, R2 V theta 2, M dot 2. And then by convention, V theta is positive if it's going in the same direction as the blades. So combining those two equations, the one we just had for the torque on the shaft and the relationship between torque and work, then also using the fact that power is work over time, so basically dividing that work equation by time and using R times omega as capital U. My shaft power, W dot shaft, is minus M1 dot, U1 V theta 1, M2 dot, U2 V theta 2. So going back to the capital V notation for velocity. You can also write this in terms of work per unit mass. So basically divide this by M dots, and the work on my shaft per unit mass is minus U1 V theta 1 plus U2 V theta 2. And obviously just divide by the M dots because they're the same conservation of mass. We can draw another form of this equation by using velocity triangles, generic velocity triangles. So I have some absolute fluid velocity V, that is the sum of my relative fluid velocity W and the fan blade speed U. So V is U plus W as seen for my velocity triangle. And then I can decompose my velocity V into V theta, which is in the same direction as my fan blade. So again, making that assumption that they're going in the same direction. These two guys are both same direction, and then that guy and that guy are perpendicular, so V theta VR, my two components of V. So using that, I know that my overall velocity, just those two components, so V squared is VR squared plus V theta squared. Then I can look at my W velocity vector, and if I break him down into a triangle, this side going up and down is the same as VR. So W is going to be VR squared plus this squared. This distance here is going to be V theta minus W. So if I take W away from that, I have exactly the other side of that triangle. So VR squared, V theta minus U squared is W squared. And then expanding this out and taking these two equations and adding them or subtracting them, I end up with V theta U is V squared plus U squared minus W squared over 2. And then I can plug that back into what we had previously. And W shaft, V2 squared minus V1 squared plus U2 squared minus U1 squared minus W2 squared minus W1 squared is another version of that formula for my work per unit mass. So the advantage of this equation is it's kind of an indication, or gives an indication of the kinetic energy losses or gains through each component of the system. So my V's are for the fluid itself, V2 squared minus V1 squared, basically the difference in kinetic energy of the fluid. U's for my fan blades, and then the W's represent what happens inside the fluid passage, so any acceleration going on inside there. So time to do an example. Have a centrifugal pump used to pump 150 gallons per minute of water. Water enters my pump uniformly and axially through a 1.25 inch diameter inlet. outer diameter is 4 inches, rotational speed here is 3,450 revolutions per minute. So it leaves my impeller radially at 10 feet per second relative to the blades. Want to determine the impeller exit width, something is called B2, we'll see that in the figure in a minute. Then we'll also want to find the torque input, so how much torque I need to supply to this pump to make it work, as well as the power required, obviously, to make it work as well. So here's a figure associated with this. So again, have my fluid coming in, left and right, into my small radius side of my pump, and then comes out radially, so VR2 basically, you can see there, coming out straight up and down, radially from my pump. B2 also you can see down there in the bottom right, so I want that as my exit width. That's the first thing we're going to find. So for the solution to part A, we can go back and look at the control volume, kind of drawing it here again. I have velocity coming in, velocity going out, and so basically just conservation of mass. Rho 1 V1 A1 equals rho 2 V2 A2. So I can cancel my rows, have water, same density. So V1, area 1, so the area of this circle coming in here will be pi R1 squared. And then where it comes out, this area here, I'm looking at basically that around area. And so I have 2 pi R2 times V2, as my area that the fluid is coming out of. So again, my fluid is coming out of this area all the way around. Fluid is going into that area, so going into a circle, coming out through that cylinder, basically the side of the cylinder. So rearranging that, I have the flow rate. So B2 is Q over 2 pi R2 and V2. Flow rate is 150 gallons per minute. Radius is 2 inches. Velocity is 10 feet per second. That to make all my conversions. So 12 to get my radius into feet, and then 150 gallons per minute, 0.134 feet cubed per gallon, and 1 over 60 seconds per minute. Brings me to 0.32 feet, or 3.84 inches, as that distance B2. Then for part B, you want to find the torque required to turn this thing. So general equation for torque, shaft torque, minus R1 V theta 1 m dot, plus R2 V theta 2 m dot. Technically m dot 1 and m dot 2, but it's the same, so I just call it m dot. Now in this case, V theta 1 is 0, so remember my V thetas, all I care about is the angular component. If you remember the diagram, when I was coming in in technically the z direction. So V theta 1 is 0, all I had was Vz. V theta 2 was omega times r, so that guy actually has an angular component to him. So this first guy is 0, all I'm left with is the second guy. So V theta 2 is r2 times omega, so omega r2 squared. Then m dot is density times flow rate, rho times q. And so I know all that stuff, so omega was 3450 RPMs, R2 is 2 inches, square that, density 1.94 slugs per cubic feet, and then my flow rate of 150 gallons per minute, and then I get to make a bunch of conversions. So I have per minute here and per minute there, so I need 60 seconds per minute on the bottom squared, the two of them. This 2 inches for the radius gets squared, so I have 12 inches per feet on the bottom, also squared. And then revolutions per minute, I need to get that into radians. So to get that into radians, I need to multiply by 2 pi. And then finally, my gallons, need to get that into cubic feet. So 0.134 cubic feet per gallon takes care of all those conversions. And I'm left with 6.52 foot-pounds of torque. And then finally for part C, I want to find the power required. You can find power by taking the torque and multiply it by angular velocity. So again, similar to the linear version of power, force times velocity, I have angular force times angular velocity. So my shaft torque, just found that at 6.52. Angular velocity, 3450 RPM. But again, change that into radians, so 2 pi radians per revolution, and I need that in per second. So divide by 60 seconds per minute there. Gives me 2360 foot-pounds per second, or more standard units of horsepower. Divide that by 550, gives me 4.28 horsepower.